So hi everyone, my name is Nick, and today we're going to talk about the paper that came out 3 years ago, and it was a pretty big deal back then. So it's called Human Level Control through Deep Reinforcement Learning, and it came out of the DeepMind company that got acquired by Google. And what we're going to look at, we'll first look at what is the problem that they're trying to solve. We'll look at action value function, the way that paper adds to Q learning, so action value function Q, and the way that the paper adds to Q learning, which is a reinforcement learning algorithm. We'll look at training details, how they train the model, the algorithm itself, the results, and then we'll have a summary and some discussion points after the break. So let's go to it. The paper fundamentally deals with this issue of how do you create an agent that's capable of performing some tasks within an environment. That's the goal for most reinforcement learning algorithms, and specifically what they wanted to do is they wanted their agent to do well in a variety of settings, in a variety of environments, and also that these environments would be challenging, at least for humans. These environments, or the tasks that they set out to solve, were games in the Atari 2600 platform. Here's one example, the Breakout Game, probably one of the most famous ones. And they wanted to teach, so here for those who don't know, you control the pedal. You have a ball that's oscillating back and forth. When the ball hits these blocks, you get some score. And your task is to move the pedal so that the ball doesn't go beyond the edge of the screen. So the ball should always, you should move the pedal so that it kicks off the ball. So this is one example. There are 48 other games in the platform. We'll see some more examples of that. And this is one example of a problem that they were trying to solve. How do you teach an agent to do that? So to formalize this problem, you have an agent, which is some computer program, or you can have a human agent, obviously a player who plays the game. But an agent selects some action from a list of possible actions. If you're moving the pedal, your actions are move left, right, or do nothing. So you have some possible game actions, and there are 49 games in this Atari 2600 platform. Some of them have just a handful of actions. Others have a greater variety of actions. So what your agent does, it selects an action, and it sends it to the emulator or to the platform. So basically, push the button, and the pedal goes to the left, to the right. So emulator executes that action and returns some new state of the environment. You change the environment by performing an action. And one change could be that the pedal moved this way, the ball bounced back, and so on. And in their quest for having so one thing they wanted to do is to have a generalizable agent, the one that you wouldn't need to tune that much to perform each of these 49 games. And the way they went for generalization was the input to the agent, the description of the environment, was just the image. So you have the screenshot of what is happening in the game. There are other toy kind of, so just like the MNIST data set is a toy data set for machine learning, with reinforcement learning there are different toy environments where you have different representations of the environment. So there is, for example, the card pull task where you have another platform actually, and your goal is to balance a pole that's attached like it's not fixed to the platform, but it kind of oscillates, and your goal is to move the platform so that it doesn't fall. And there, the representation of the environment is the position of your pedal, the angle of of this pole. So this is very environment specific. This representation of the environment is very environment specific. What they wanted to do is to have, again, an agent that's capable of being as general as possible. And the way they did that was going for the representation of the environment as an image of the current screen. So you send an action to the emulator, it returns the screen, and it also tells you how your action changed the score of the game. That's the reward that you're getting. So there are three important concepts, or three basic concepts in this whole reinforcement learning thing. One is the action that you perform. The other is the state of the environment that you're observing. And the third one is the reward that you're getting. The reward could be, your actions might not have an immediate reward. The reward that you get at this point might have been influenced by something you've done 10 episodes or 10 game steps ago. So there's one of the challenges is to figure out how do you match the reward with some of the actions that you've done in the past. And this is what the emulator returns, how your action changed the score. The goal of the agent is to maximize future rewards. So we're looking at the current state of the environment, and our goal is looking into the future to maximize this the reward, in this case the score. One kind of tweak is that we could sum up all the rewards that we expect to get into the future. But that would lead to, if our game goes on forever, we would get a return of infinity, right? So our future reward would be an infinity. So what we want to do is we want to discount the future rewards. So one reason is because we would have a limit on the future rewards. The other reason is that the environment might be stochastic, and we can never be sure that the reward that we're going to get in the future is what we predict we'll have. So we need to discount our estimate of the future reward. Right, so action, state of the environment, which is an image, and reward, which is the score.
Okay,
yeah.
We go back. With the sum, T prime and T aren't really are the power, or are they the superset?
No. This is you start at the moment of time T.
Yeah.
And you go on until the episode terminates.
When you subtract, what do you mean by subtraction? Are they the power
this is the power? Yes. So you raise. This is the gamma is smaller than 1, and you raise gamma to the increasingly large power, so that the gamma itself in its power diminishes. This term diminishes as you go further into the future. So this is how you discount future rewards.
Gotcha.
Another question.
Yep.
So the score is different between each game, yeah? Am I right?
Yeah.
No, not the same.
Each game has, some games would have a score on the order of thousands, some might have a score on the order of tens. And we're actually going to come back to that. What they do is they clip the score so that if there's a positive score, they just max it out at 1. Okay, so how to teach our agent to achieve that maximum reward and tie reward to the state and the action. We can define this optimal action value function, the Q with an asterisk, as the maximum expected reward that we're going to get given the state that we're in, the action that we take, and kind of the policy that we're pursuing. And you can think of a policy as something that just maps states to actions. If we're in the state, we choose this action, and this is how we describe a policy. Yeah.
Are policies usually just a set of rules, or randomness to them?
there are different. You can have a deterministic policy, where you always pick a specific action. So if you are in a given state, you would always choose that action, a specific action, no matter when you encounter that state. You could also have stochastic policy, where within, if you have the same state, you might choose actually different kinds of actions.
So usually people pick in between the two, or use
it
one
really
or the
depends
other?
on the task. So for example, it makes sense, like in the game of poker, it sometimes makes sense to have a stochastic policy. Like when you're bluffing, for example, you don't follow the deterministic policy. There are other ways of introducing randomness in your actions besides having a stochastic versus deterministic policy. You might have a deterministic policy, but not always follow it.
Right.
So sometimes you might choose a random action just because.
And another quick question. So, so is policy then where we implement exploitation versus exploration?
That's.
Are you getting ahead of the?
I could be.
Yeah.
You probably are. Yes, you probably are.
Because
Yes.
you were reviewing the whole slide.
Am I? Okay,
Yes.
sorry.
Breaking your own rules.
I know, right?
I was in the TDLS actual mode, not classics mode.
So you can rewrite this equation as the expectation over, so S prime is the state, the next state that you're going to get into, and the expected reward that you're going to get from that state. And you would have, after you're in a specific state, you take a specific action, you will get a specific reward from that action, plus you want to get the future discounted rewards. So in other words, your reward for taking an action in a particular state is not just the immediate reward you're going to get from taking that action, but also these discounted rewards that we spoke about, that we saw in the previous slide. Yeah, so this is known as the Bellman Equation, and pretty much like 5 minutes after you see something on reinforcement learning, Bellman Equation is probably going to come up. So that's what it is. The idea is that your goal is to maximize your future discounted returns after you follow a specific policy. So I think in kind of intuitive terms, you want to find a set of, you want to be able to choose an action. Once you know a state you're in, you have to be able to choose an action. And this action value function is a way for you to choose that action. Okay? You can represent this function in different ways. For simple environments, you can have a table that lists all the states that you can possibly have in that environment. The actions that you can take. And then for every state, you can say, you can put a Q value for different actions. So this is one way in which you can describe this Q function.
Can I ask 2 questions?
Yeah.
I promise it's about this slide. So, is that equation then recursive, or because you seem to be?
Yeah.
Okay.
It's this is the ideal policy that we're pursuing. So in other words, we assume that we have this policy. We're operating under certain choices of actions for certain states, and if we follow that policy, then we would be able to get that discounted reward. You don't actually calculate it as in a recursive way, so but it's something of an intuition that you might want to have.
I see. And what happened to pi?
Pi is, it got incorporated here because this is the optimal action value function. So the Q star assumes that you're following an optimal policy, meaning that an optimal policy would be the one that maximizes the expected reward for the actions that you're taking.
Is this is this model like specifically designed for a game which follows additive scoring?
No. This is a generic representation because you can formulate many, a lot of problems in this way as an environment, state in the environment, an action that you take, and the reward that you're getting. So, for example, if I want to open a door, this is my environment. The actions I can take is walk right, straight, left, right. And the reward that I'm going to be getting is when I get and open the door, I will get a reward of 1, right? And some actions, and if I don't open the door, I'm going to get a reward of 0. So my task would be to find the optimal policy so that if I follow that policy, I would eventually come to the door and open it. So it's a way of representing formalizing many problems.
So I was thinking, like in the previous slide when you had the thing to optimize future rewards, so that's like an additive thing where each step has a reward, and you weight the future rewards originally and you add them up. There could be games, for example, where the score or the reward that you get at some point that has both a good and a bad thing about it. Like if you have a very high score, you could lose all of that and like get a negative or something. So those are not linear models. So are you saying like this should cover those as well?
Oh yeah, there could be negative rewards because so one way to formulate the problem of opening the door could be having a reward of 0 until I open the door. Another way of formulating that could be if I start walking away from the door, I could start getting a reward of 0, right? And if I walk towards the door, I can get a reward of 1. And when I open the door, I could get a reward of 10, right? So, and actually, designing the reward well can make or break the reinforcement learning problem. Because
So I think what this means is that the small r of t is not necessarily a linear function. Like it could have very nonlinear functionality versus t, right?
R with respect to t, right?
A small r of t.
R of t is a function independently. He can depend recursively.
Yeah. So that's what I'm saying. Like if it was additive, that would be a very specific R of t.
Fair, yeah, that's
like even the coefficients. Like the only thing that you need for the coefficients is the convergence of that series of infinity. Otherwise, if it diverges, then you can just keep playing the game and you have infinity.
Yeah.
So the value Q is like the maximum value that you choose from a table that you mentioned, like S and A. You have states, you have actions, and then Q that will be computed for each of that state and action.
Right.
So the max Q will be the action that
for a given state, the maximum Q would be corresponding to the action that would give you the most reward in the long run.
So that action would be the one which we will take, which has the maximum Q. Right?
Yeah. So this is how you decide. You can use that Q function to decide which action to take, and one obviously would be to take the action that has the highest Q in a given state.
Yeah, you talk about the reward could be a negative. I think the reward is the flip side of the loss function. And then if your reward is negative, the loss function will be positive. How do you train your model if your loss function is positive?
Well, let's get to the loss function because we'll have it in a few slides. Okay.
Can I ask?
So I have a question regarding the formula. So in the previous slide, if I just want to calculate the rewards in the current state, forget about what's going to happen in the next state, then the result would be just I'm not sure how you pronounce that sign, but let's say
this one.
Yeah.
Gamma.
Yeah.
So that is equal to gamma for the current state. Am I right?
For the current state, it's equal just to the R, to the reward.
So then if I just having a T bar is equal to 1 to 1, the result is R or gamma?
If it's from 1 to 1?
Yeah, 1 to 1. I just want to look at the current state. I don't care about the...
in the current state, you would have the R. The R, the reward that you're going to get.
And then why in the next formula I have R again?
Mhm.
Because you see I have R plus gamma. So
Yeah.
I'm not sure why we have this R here.
This is the R that we will get if we take this action in this state.
Okay.
Oh.
And this is the current reward.
Yeah, that's the current reward. In fact, if you set gamma to 0, then all you're going to be looking at is the reward that you're going to get in the next step, on the next step. You would have you wouldn't have kind of long-term planning from the agent, because it would only be looking to maximize the reward that it's going to get on the next step. So this is a way of introducing this kind of longer-term behavior.
So you mean that in this gamma I don't have the current state reward? Am I right?
That's the
in the gamma there is no value for the current state reward. There is no R in it.
That's the reward you're going to get on the next state. Yeah.
Gamma is a constant, though, right?
Yeah.
It's
It's a parameter that you set.
I think what he was saying is that it's not superscriptive, so it's for this step.
No, I'm trying to just to understand the formula. So.
Right. Yeah. So so this doesn't actually use the previous page's formula.
It
Just
uses
directly.
as capital R of
Here.
T.
As capital R of T, okay. Yeah. But hold on, but that doesn't exist in the right side of the equation.
here.
Yeah.
These are your future rewards. You're following some optimal policy, you're assuming,
Yeah.
and you're taking in the next stage, you're taking some next action. You're going to get some Q out of that. So that's your next, and you're going to get a reward from taking
but
that
you're
optimal
not
action.
computing RT anymore.
Well, if you
That's
solve the
the-
first line, you get the second line, right? So if you insert capital R of T from the previous
I
slide
thought-
and solve it,
Yeah, exactly. So you expand that.
I thought the idea was to solve the
This-
second one to get the first one.
So you only use it
I don't
once?
think it's-
No, you can solve it. Just substitute RT. Go back to the previous slide.
Yeah, this sounds good.
And you write the summation equals to RT plus summation of T pi equal T plus 1
Yeah,
to T.
exactly.
It's a recursive.
So you can
And
you
the
can take
gamma,
the
same thing.
reward for the current state out of this, because on the
Yeah.
first the episode that you're in,
Yeah.
gamma is going to be equal to 1, right?
Yeah.
And
And
you're
then
going
you
to have
just
the reward.
substitute back to the next
Yeah.
page, which
Yeah.
is the same.
Yeah, makes sense.
So your RT becomes R plus gamma, and you're finding the same thing, maximum of Q value for the next
Right.
step.
Right. Now just one last question. Q, like the BQ, S prime and A prime, so that Q is a function that returns multiple S primes and A primes, or
That is Q is a function that gives you Q values for a specific state and specific action. So if you go for in the next state, you might have a certain set of actions. You would have certain Q values associated with these actions for the next state, and you would take the maximum Q value out of those.
because maximum only it makes sense if you have a set.
Right. So you would have a set of actions, and for each of these actions, you would have an associated Q value.
So then the product of Q is a set. Then it's not one-to-one, right?
The product
The
of
dot
Q.
product of the result of that Q. If you run the function Q, you get a set
Mhm.
of actions.
Yeah.
Some of them optimal, some of them suboptimal. You pick
Right.
the optimal.
Yeah. Okay. So here's an example. A few states and the Q values, the action value functions. This is a game of Pong where you're controlling this paddle and you're playing against a computer opponent, and your task is to, again, bounce the ball back. So you're moving the paddle and you have 3 actions. You can do nothing, you can move it up, you can move it down. And you can see how the Q values for each of the actions change depending on the environment, on the state of the environment you're in. So in this situation, so these traces are they're not in the game itself. They added for this visualization to see where the ball is going. So in this action, in this state, all actions have pretty much the same values. As the ball keeps going up, the Q value for the up action starts going up, and now you really want to hit the ball, so the Q value for that action is also high. And when you scored, then again the Q values for all of the actions are the same. So this is how, again, you're in a state, and for each of the actions that you have some associated Q values with these actions.
So what do you do in cases that the Q value is the same?
That's a good question. I mean,
Randomly pick one.
yeah, just flip a coin. Yeah, exactly. Or yeah. Here it doesn't make. Here you're not actually probably taking any action because the game is going to be over. It's probably going to be over in the next step. So where do we get this Q star? How do we? Where do we get it from? Well, instead of this, this is what we had under the expectation in the two slides before, right? The reward plus discounted future rewards. So instead of this optimal values, which we don't know, we can use approximate values, and we can use some set of parameters theta to approximate target values for this state and for these set of actions. And one way of having these parameters, parameterizing these thetas, is through having a neural network, and thetas would become the weights of the network. Another thing here is that these thetas we're taking them from some previous iteration, and as we'll see in the next slide, what we want to do is we want to learn, keep learning these thetas, keep updating these thetas. But the takeaway in the slide is that we're using a neural network as an approximator for these optimal Q values. This is the loss function.
Question.
Yeah.
Why we cannot calculate the optimal value?
Because for some instances you can. For some instances you can go through all of the states, take all of the actions, and see what reward that gives you. But it would be very limiting. You would have to operate in a very limiting environment. Because if you work from pixels like this, you would have a huge number of possible states. And you cannot visit them all. So you have to approximate them.
So then, I'm not sure if the discussion is a lot of time or not, because you have the signal that's from the current state to the couple of the following states.
Right, right.
So what's the windows that you are talking about in terms of the paper? How many states in ahead of the time you are looking at that you think that okay, this is not possible?
You're talking about this one.
Yeah. So what's the maximum of the T?
T is where your episode terminates. Yeah. So this is where the point where you, for example, score or you lose the game, right? So this is.
And then on the next slide, you mentioned that this thing is not possible because the capital T could be used at the time, and basically computationally it's not possible that you can have the things.
Yeah.
That's why you're going with the
Yeah.
T bar. So I wonder that what's the number of the capital T?
So it's autoregressive, right? Say you can only, if you go to the picture where you're showing the Pongo, yeah. So for each, say you can, there is like 10 slots on the screen, only 10, right? Each time you go ahead and you go ahead through time, then it's like second time is 2 to the power of 10, and it gets exponential. So 10 steps ahead, now you have 10 to the power of 10 states that you could have ended up, looking at if you want to look at the result. Does that make sense?
Yeah.
So then the capital T max is 10.
No, so capital T is just number of time steps, right?
No, I'm trying to understand that because you said that these things are not possible to calculating it, so I wonder that okay,
Yeah.
probably
So
there's
that's
a
what-
computational issue there, and then the computational issue is based
Yeah.
on the number of the so what number we are talking about?
That's why instead of doing this summation into the future, you have if you expand that then all you need to do is to get the reward in the next step, and then discount the Q value for the next step. That's all you need to do. So you don't need to look into 10 or 20 steps into the future, because all you need to do is just take the maximum value of the maximum Q value of the next step, and
And then the
with
maximum
the
of the other one and the other one.
just the next one. Because this one would incorporate the future ones as well. Because the assumption here is that you're following some optimal policy. And if you follow that optimal policy, then the reward you're going to get at this time step would include all the future rewards, discounted future rewards.
So I'm trying to understand, well, I mean, related to that question, the scaling that Esna talked about. So what is the scaling of this computation that you're doing here? Essentially in, capital T, and the size of state space, I believe that would depend. So is it exponential in these two, or?
No, you're only looking, the reason why we're doing this is that we can only look into the next step, and we can ask our neural network or whatever approximator we have. We can ask our neural network. So, given the state that we're going to end up in, and given the action that we're going to take, or if we can actually just pass the states and give us the Q values for all of the actions for the next state. And our network will have some parameters, and it would output the Q values for all of the possible actions in the next state that we'll end up in.
So I thought you asked, where is the bottleneck, computational bottleneck? And my answer was the state space.
Your answer is correct. Yeah, I think also that it's not exponential. It's like the binary trees, because there is a pixel and there's an action. So the pixel going to change and also the action going to change. So basically, by each action, I just having the 4 possible situation in the
Are you
picture.
talking about with neural net approximator or
No,
without?
without.
Without it is exponential, because if you have, if you want to look back into in time, for each time, you have 10 different states you could have picked. Second time, you have
a state. No, just for a state, because think about the number of the pixels that's going to change.
It depends on the
each
game.
step,
it depends how you set it up.
one
It depends on the
pixel,
game.
one pixel changing. So
It depends on the game, and in general it will be exponential, because every action it grows just you multiply the number of actions.
Yeah, depends on the game. Like if it's just go up or down, yes. So the space is 2. Is again, it's 2 to t, basically. If it's hold on, is it correct?
It depends on the number of states, right? On the
Time to the size of state.
Just think of the number of different sequences that you can have of t elements, right?
Yeah.
So if you have 2 in each step, and you have 2 here, 2 here, 2 here, 2 to the 10, 2 to the t.
Yeah.
That's if you have 2, but there are some games that you will have 2 actions in the first one, then in the second one you have 5 possible actions, then in the third one you may have only 1, and so on. So the space changes, it can vary a lot.
I think it should be much higher, because only with the pictures, you didn't know the underlying and the physical equations, and so for the pictures, much higher.
Okay, I'm gonna edit this. We've really taken it.
No. That is good. So the loss function is we take our neural net approximator, or whatever approximator we have, and we use the weights from some previous iteration to calculate the target values. We multiply them by this discount factor gamma. We add the reward, and then this is the target value, and then we check what is the value that's predicted by the network for this state and this action. So it's pretty much like a supervised learning problem, where you have only instead of labels, this is your neural net predictions, And this is the kind of true labels, only you don't use true labels, you approximate them with weights from a previous iteration. And you take the squared sum of that, and that's your loss, the expected value of that. This is the gradient, so you take the derivative of that, and you go from there.
Was that clear? Okay, I was just seeing if it's just me. Okay, so I didn't pay, it's my fault, I didn't pay full attention. So you have theta bar now?
Yeah.
So your S prime and A primes are your next step, right?
Mm-hmm.
And then S and A are your
current
either current or previous current step. And I'm trying to see, so both are neural nets approximations?
The second Q is ground truth, right?
This is what you're predicting.
Oh, predict.
And yeah, and this is the your prediction of the ground truth, your kind of target value. That.
But you're fixing the parameters.
Yeah. So these parameters theta are not the same as here. So you're taking these parameters theta from some previous iteration.
So is it easy to think that your neural network at every time step is giving you a Q function for all the actions, and you're storing the previous time step action, state, action, reward, that reward pair, and then you're comparing that to current prediction, and then kind of like that's your loss function here?
You store the weights. Okay, you store the weights, and you take the state that you will end up in if you take this action from the state.
Right.
And you take those weights from some previous iteration to generate some predictions about the Q value.
What's the right side Q again? So that's your neural net approximation for the current state.
Right.
And on the left is for the future step.
That's for, yes, this is for the future step. Yeah.
And you're seeing what the optimal predicted step, the optimal predicted action, for that future step. How is it different from the optimal for? Oh no, there is no optimal. I'm confused.
So Q is perfect. This will be zero because Q is predicting next step and we are calculating next step as well with our plus sum. So if Q is doing a perfect job, this will be zero. But now it's not zero because it's not perfect. So we train it gets trained towards being perfect.
Yeah. You update. You take these weights from some previous iteration, and then you use your current knowledge of the state that the network is in to see how your current predictions are different from the reward and what have predicted with the weights from this previous iteration. So I don't know if that makes sense.
Ideally, you want a neural net that gives you that R plus gamma max of whatever.
Mm-hmm.
And you're sort of recursively training it to achieve that.
Yeah, good question.
Same question.
Okay.
What's the architecture of a neural net?
That's probably going to be the next slide or the next few slides. Okay.
And there's one more question.
Yeah.
What do you mean the previous iteration plus theta? Because it's a different theta, right? You said.
Yeah, theta bar is, and this theta are different. So this you take from some previous iteration, and then as you train the network, just like you do in supervised learning, for example, you update the weights, using the loss function every step. Yeah.
So like the theta is like say I minus 1, the last time step.
Could be the last. This is what they used, the last step, but it could be a few steps back. Yeah.
Just a small question on notation. If I were to read this, how exactly do you say what the semicolon is? Like function Q of SA what theta?
Well, it's just that it's parameterized by theta. So you take the Q value of a particular state and action, and then the whole Q is parameterized by these weights theta. So they're kind of different in a way, because your function Q is essentially represented by these weights.
Yeah.
And this is what you're trying to learn here as well. Whereas S and A is kind of given, right? You know the state and the action, and you want to have your trained weights tell you the Q value for given state and given action.
Okay.
So it's not necessarily like an input to the function, it's like a property of the function that changes the weights.
It's a learnable parameter.
Yeah.
Okay, I'm gonna do another. I'm gonna take another shot at this, but I think I got it. So your right, your Q on the right side is what you're currently predicting, the reward that you're currently predicting for the future step.
No.
For the current step. Yeah.
But current step, you're seeing your action and your state, but you're using the same Q function. I think that's the key.
I think if you think of it like times to 0.
You guys aren't helping.
Because the max there, so it's for current state.
No, max is in the. I'm talking about the right side.
Yeah. So this is the whole. This is the error. Am I right? So the ideal format is that the Q is equals to the R plus gamma max x bar. The whole thing will be zeros.
Well, only one of them depends on A prime, so it's only that second one that has a max. So if you want to think of it, I think this might help. Time 0, everything is random. Your Q, you have like a random set of theta. You have a random set of Q functions with those theta, and then like you can actually like with S and A prime, and then you will get something. If you put those random theta parameters into the Q function, you will get a prediction for the state, current state with those, and then you compare those to your random state action reward pairs, and then you evolve.
No, I get that.
Yeah.
No, I get the machine learning part, and I'm just trying to see what exactly. So when I'm actually implementing it, what am I putting in those values? So you have S prime and A prime. They are the future. They are future steps. You have a theta, which is your previous step weights, and you have theta I.
Yeah. So you can think about this. If you think if your Q is a neural net, then your thetas, these ones, are the weights that you have at this moment.
Yeah. So they have been added the derivatives of the theta bar, of the theta bar step. So they have the next step from theta bar.
Yeah, they should have improved from that step.
Yeah, that's what I'm trying to say.
Yeah.
Why do you use same theta? Why do you need a theta bar?
The differentiable of the max functions. You cannot differentiate the max function.
Bar is the iterative, is a historical accumulator. It's not the neural network, right? Which is statistical.
Well, it is the parameters of the network.
It is the parameters of the network that you saved from. You know, you can carry them over from the previous iteration. Yeah.
So in some sense, I think what's confusing me is that theta bar is about history, and S bar and S prime and A prime are about future.
Right.
That confuses me, because I'd like to think of it this way: if you have theta bar for previous step, and then some S and A, then it makes sense to compare the future reward, which is the right side, what you're subtracting, and the prediction of the future reward.
Right.
And you subtract those, it makes sense.
Let me get a step of that. Take a step of that. And so I think this actually goes back to the question of, we have a comma here and a semicolon here. So what we do have we want to ask our neural net that was in some previous state about what does it think would be the future reward. And the idea is that you train the net so that it gives you more and more accurate predictions.
Yeah.
So that's why you want to query some previous network for the future values. And then you compare that with what the current state, what the current network tells you.
Yeah. Yeah. So I think in a sense then, yes, on the left side you are trying to predict the future values. It's just your parameters are less current.
Yeah.
On the right side you have now you have made an observation, so you're closer because you're using the exact Q function.
Right.
So you're just closer. There is there is no ground truth, right, on the right side.
Yeah, which is exactly right, because otherwise we'd be in supervised learning territory, right? If there was ground truth. So
Gotcha.
we changed the parameters as we go.
Gotcha. I think the only thing that confused me was the fact that S prime, we were talking about future set, but like theta bar was history. But I think we figured it out.
Yeah.
Yeah, I also want to see if I can get this right. So you look inside the square brackets on the first line. You've got two terms. Now you have to think of the reward as this cumulative thing that you get.
Could you speak louder, please?
So you're playing the game, and you get reward each step. And so the reward has to be thought of as this like bag that you're filling up. That it gets bigger and bigger over time. And you've got two terms there. On the left, you've got the actual reward plus the discounted sum of rewards so far. And the right side represents what you actually got. So you're comparing, hey, I did this thing, and this is the reward I got. Here's the discounted total reward in the bag plus what actually happened. You take the difference of those two. So it's like a supervised learning task in that you're comparing the outcome that actually happened plus the discount of everything that happened before to what in fact happened. And you're seeing if you can minimize that difference.
Yeah.
So that the policy becomes good at tracking what the environment actually provides in terms of rewards, and you can get closer to a better reward. Is that more or less correct?
Yeah. Yeah. The idea is to basically make the network predict the Q values so that essentially this becomes zero, right? So that you your prediction for the next rewards is the same as your actual reward plus the discounted rewards in the future.
I have an argumentative question, which is what tries to ask. I'll keep it later. Which is why don't you just use theta I minus? No, I don't want to discuss it. Just like
Why
that's
don't you use
confusing.
theta? What's the question?
Yeah, why don't you use theta?
You need a gradient. You need some difference between what you predicted and what actually happened. And if you don't have both theta minus and the theta, then what do you do? I think this is the comment before, but what do you differentiate?
What are you trying to improve? Or how you're going to know how to improve?
So when you're adjusting weights in your little epsilon steps, you've got to know which direction to move in, and that's what gives you that difference.
So theta minus is just a way of highlighting the fact that one is closing the other is you're changing it.
This is in my brain how I look at it after asking all these questions. So I'm here, I think I'm going to get a lot of rewards, for example, if I go there. Right? I have some set of parameters right now, right here. When I go there, I can observe and I have some better parameters now. So I probably make more accurate predictions. And the difference between the two will be my loss. If I have the same parameters, then what am I haven't learned anything. Okay, that didn't help. Help me.
Yeah, okay. All right, so let's just go through some of the, this is, what we've been talking about so far is the kind of the Q learning algorithm. So you have this action value function Q, and you want to learn that function somehow, so that you know, given a state, which Q values are associated with each possible action. So what the paper added to this Q learning are three things. The first one is the convolutional network that they use to pre-process the images that we feed into as a state into the network. The second one is experience replay, and the third one is they added another network, which I'll talk about in the next slides. So this is the convolutional network that they were using. Basically, what you're feeding as an input is these raw pixels from your simulator. They actually pre-process it which I'll talk about later. And then you have the picture from the paper shows 2 convolutional layers, but they actually have a third one here. They have 32 filters, 64 filters, another 64 filters, a fully connected layer, and then the output layer where they have the number of units the same as the number of possible actions that you can take. And this layer, what you have in this layer are the Q values for the state that you're feeding in. So Q values for the actions that you can take in the state.
Why are there 2 series of them?
Here?
The final layer? You seem to be repeating sets.
Because you have the button, so you can press the button and move the joystick as well. Yeah, and then you can also do nothing. So there's the kind of no op, and the others are list of possible actions. This is what they did was they looked at how the last hidden layer, how the values are represented in that last layer, how the values of different states in the game are represented in that layer. And the states are, again, screenshots of the game, and the blue dots are low value states, and red dots are high value states, even more so as you go. What they wanted to show with this was that kind of perceptually similar states would be close to each other. So they ran it through the TSNE, and this is what they got. And perceptually closer states are close to each other here in this TSNE representation. But also, they pointed out that, for example, this and this state are very close to each other, but they're kind of, you see these orange things here, which are not, so the states are not as similar as, for example, these ones, but still they got mapped together. An explanation they had was you're getting to the end of the round here, the goal in this game is to shoot all of these blue dots, all of the yellow dots, I'm sorry. You're standing here, you want to shoot all of them. And you're almost done, and these somehow don't matter as much for the gameplay. So this and this state, if you disregard the orange things, this and this state are pretty similar to each other. Yeah. They had 512 units in the last hidden layer.
So 512 times 500.
They took all the pictures, they look at the embeddings in the last layer from the picture, they look at those embeddings, they use TNSNE to dimension 2, and then they just pick it.
We have a very good video on this. Coming up.
So, can I explain other ways, like there are some regions of very hopeful state, and there's some just hopeless situation?
Yeah. Yeah. So there are some states in which the network expects that it will get a high reward. So this you want to be in these states with the which are red dots. You don't want to be in the blue states. So that's one thing that they did, was they added the convolutional network. This is why it's called the deep Q learning, because the deep comes from that convolutional network. Another thing that they added to Q learning was experience replay. And this is where they collected the transitions of the current state, the action that we took, the reward that we got for taking this action in this state, and the next state. So you collect that information and you keep a history of that. You keep some kind of a buffer. And they had a buffer of 1 million most recent transitions like that. And when you train, instead of training on only the recent experiences, you take a random sample from here. They had a mini batch of 32. You take a random sample of that and you train the network on a random sample of these experiences. And the goal is to reduce correlations that you will have if you go from one state to the other. Neighboring states are going to be very highly correlated to each other, right? So you want to remove that. They first let the network play for 50,000, just make some random moves, and start populating this replay memory. Yep.
So they save the like time-wise motions. How does it work? For example, if there is a state, we cannot jump to something random.
Could you repeat the question? I don't think the camera got it.
So you're asking, did they save the timeline? Did they save like the progression of steps they take? Yeah. So you are in a state, you take an action, you observe a reward, you see the next state, you take that and you add it to your buffer. You do the same thing on the next step. So you're constantly, your buffer is a history of what you did before, but you don't use that history as, so you take random samples from that history. Yep.
And those samples are fed into the Q-learning algorithm, so every, like the SNA you feed in are those samples.
That's how you update your network. Okay.
So 1 million, right?
Yeah.
So 1 million previous time steps.
Yep.
And I think the idea then is you inject noise because the previous step would be highly, again, as you said, correlated.
Right.
So you just picking up something that happened like a while ago, but you added. But are they really relevant? Is that argumentative?
I guess depends on the game.
Yeah. Okay. We'll talk about it in the discussion, but
you so another reason why you want to have that. I don't think the network doesn't care about which state you're in right now. All it cares about is these transitions. All right. You want the network to predict, given the state, what are going to be the Q values for the action, and whether it's something from right now or from the recent past or from something that happened a million time frames ago. Doesn't really matter. All you care about is these transitions. You want it to be able to predict the Q values correctly. If that makes sense.
Yeah, I'm just so 1 million most recent combination of S's, A's, R's, and S primes. All I'm saying is that like something that happened a million time steps ago.
Yeah.
Does it actually is it actually relevant? Like do we?
Yeah, because you took some action in a particular state, you observed some reward, and you still want the network to be able to predict correctly. No matter whether it happened a million steps ago, because you actually might come back to that state, right, at a later point in time. So you restart the game.
Right.
You win or you lose the game. You restart the game, and you might end up in the same state again.
Right.
So you want to be able to predict
what happens
for a given state. Yeah.
A long time in the future, perhaps. Is that what you're saying?
So it's not within the same game. You store for different
Yeah.
games, right?
Yeah.
You just keep the history.
You could just keep the history. And so because all you care again are about our transitions, and this way you can actually increase the use of your so instead of just using, for example, recent experiences and discarding them, you actually store them and you can reuse them. They would be reused probably multiple times because you're drawing a mini batch of 32 and you store the 1 million most recent ones. So you would have a higher some of these transitions would be sampled more than once. So you use your data more efficiently.
So our time steps, are they frames?
Yeah. Well, I'm going to come back to that in a sec, but you can think about them as frames, yes. Yeah.
And when we sample, so we're sampling randomly from time, right? So I think it doesn't sit well with me because there could be a huge gap between these time steps.
Yeah, that's my question too. But like, is the answer to that question that when you say a random mini batch, like you essentially grab, say, 100 frames from one place that are sequential?
Yeah.
No. You just randomly grab them.
Actually, it's predict the next state, not predict Q value. So whatever is always same, right? So even it could be a stochastic. I mean, if it means
so that is stochastic. Yeah, that's what I'm trying. So you're just adding stochasticity to your input data.
Well, what you want to do is you want to predict. If you were, you're not trying to predict the future from the recent past, right? You want to train your network so that it's able to start a game, and that would be one state when, let's say, all of the tiles are there. You want to be able, the agent, you want the network to be able to finish the game, to see it all the way through, so that, well, all the tiles are gone, and it finishes the game with the highest score. So there's a whole bunch of states there that the network will experience. And you want the network to be able to learn, given a state, no matter if it's from something that we played 5 frames ago or some time ago, what was the reward that I took in this state for a particular action, and which state did I end up in?
Right. So each certain action that is informed by a random sample of rewards and everything from some history.
Yeah, but then at the same time you're training the weights of the network, so your network is getting better and better at predicting it.
Yeah, fair.
Yeah. Sure.
What is the policy? You have mentioned. What is the policy? Policy is always just to take the action and maximize the Q.
Yes. So you assume you don't have a in Q learning you don't have an explicit policy. You're assuming that you're following the optimal policy.
Is there any randomness in this? No, always max.
In 2 slides.
Okay.
Okay. All right. Any other questions here? The third addition that they made was they actually created another network for predicting the target values. So these values that we the network that we use to generate targets that we compare what the network currently predicts on. They created another network and periodically reset it to the network that is being trained. And the goal is the idea or the rationale is that if you if you increase the Q of a particular action in a particular state, that would also increase Q values for the next state for all actions. And if you just keep using the same network for which is based on the recent updates, then it could diverge. So the Q values could become really high. Yeah.
So where the theta bar comes in?
The theta bar? Yes. So this is the network that you use to for the theta bar. Yeah.
Did you say what Y is?
Yes. Great question. The Y is the reward plus. Just scroll back. That's Y. That's your target that you're generating.
Okay, so sorry. Can you hold on 1 second?
Yeah.
That I know what is. So you use 2 separate networks to generate the first term in loss function and the second term?
Yeah. And you do that for a while, and then you reset this first network to have the same weights as the network that you're training.
And what is the advantage?
The advantage is that if you use the same network for generating predictions, let's say you use the weights from the previous iteration that we spoke about, then if you have a Q value for this step, or if you choose an action that maximizes Q, then it would impact the next state. The Q values for the next state, they would also be higher. And you can just end up in a kind of a loop like that, where your Q values are just going to be higher and higher, just because you're estimating your Q values based on the recent experience from the recent
It's
iterations.
a ceiling on the loss. Over time, it puts a ceiling on the loss because this decay function applied to everything before is frozen, and so for a while the losses aren't getting bigger based on the some sort of cascade of stupid decisions and stuff. it's a ceiling on velocity because it's that second term to what you're having to the current reward estimate your first term velocity.
So does it mean that you're training the two networks at different rates?
I think the Q hat should not be thought of as a separate network. It should be thought of as a tool to slow down your loss function. It's like, think of it as like drag on your loss function. I mean, it's just you copy out your thing and freeze it out your thing. Like instead of always using the previous time
Right,
step.
so essentially you're training them at different rates. Because you said you freeze it for a few steps, which means that you don't know.
Yeah, I don't really think.
But you don't train this network.
Yeah, yeah.
Right? You just take you
just
take
copy
this.
over.
Yeah, yeah.
I see. So you copy parameters from the network that you're training, say every 10th step or
Mhm.
whatever.
Yeah.
So Q hat isn't trained?
It's just a copy of this at some time step. So it, you don't train this explicitly, but as Q gets trained,
Yes.
this one gets replaced.
Every few times
Yeah.
it gets reset. So every few times the training gets reflected at Q hat.
Yeah, exactly.
How do you choose the time to?
Yeah, so they do it every 10,000 frames. The way you choose that, you could do just hyperparameter search. They went for what they call informal search, where they just did that. It worked, and they stuck with it.
So you have 10 more slides.
Just one quick clarification. I don't know if I missed this. So this, like the theta I minus that you had, is actually not the immediate previous set of parameters, but it's some time much further in the path.
Yeah.
That's what you're doing.
Yeah.
That clears up the last slide a lot.
Okay. Good.
That old one.
Good. Yeah, try to make it as complicated as possible.
Could
Just let you guys ask questions.
Could you repeat that point for the camera?
So the theta bar that we saw in the
So theta bar was not from the immediate last step.
Right.
It was potentially from 10 steps before.
Yeah. So these are the weights of the Q hat network. All right. What they did also. So I think we're gonna go faster now. Yeah.
Very quick question, but A prime and S prime therefore the very next step after.
Yes.
Okay.
Yes. Yeah. That doesn't change. That's why you have this difference between S and A, which are things you want to learn about from the Q function, and theta, which is what you train from the Q function.
Gotcha.
So this is a table that they have where they switched off both experience replay and this second network and showed how that affects performance. And they did it on a few games, and these are the scores that they achieved with both experience replay and the target network. This is where they switched off the target network, they switched off the experience replay, and they switched off both. What they show here is that performance goes down on all of these games. So the point is that it matters, right? Both of these things matter.
Replay is the most important.
Huh?
Replay is the most important.
Yeah, probably. Yeah. Yeah. Okay.
With the replay, just correct me if I'm wrong, but don't you abuse your memory such that you store so much information of what happened in the past? It's almost as if you're memorizing every possible thing that's happened. I'm just kind of confused how replay.
Well, you're not using it, right? You store it, but you're not at any given point in time, at any given update, you're not using the entire all the million.
You sample it, right?
Yeah, and the
But
sample
use
size
it
is
to train the
32.
network.
So
You only use it to train the network, so you're not really remembering. You just remember your weights. So your network is.
What exactly gets stored in that cache? Is it the rewards from that transition state?
well, it's the state, so the screenshot, the action that you took in that state, whether you move the paddle up and down, for example, the reward that you got for moving that paddle, and the next state you ended up in.
And then for every step we take the current state plus a mini batch of those previous ones and use that as the way to train network?
To update, yes.
Okay.
Yeah. these are the training details. They used ARM as prop, and they used an epsilon greedy policy, which is a way to introduce some randomness into, or some exploration exploitation thing. So we want, originally because we set the weights at random of our network, we want the network to explore a lot. We want it to explore as much as possible in the environment. So we have it play at random, and the epsilon determines the rate or the probability with which we select a random action. So we originally start with 1, so all the actions are going to be random, and then we gradually anneal it, reduce it to 0.1 for the first million frames in the training, so that we increasingly are choosing the actions based on our network predictions rather than randomly.
So it's a probability, epsilon.
Yeah, epsilon is the probability of choosing a random action at any given state. They trained for 50 million frames, which is the simulator runs at about 60 frames per second, so that's about 38 days of playing. They also pre-processed input. The pictures I showed you are not the thing that gets fed into the network, so they scale it down to from 210 to 160 color images to 84 by 84. They convert it to grayscale, and they also do some things like they don't take a frame from a particular step. They also take the neighboring frame because the emulator, the way it was created, it has some kind of flickering, meaning that some objects are only there on odd frames, some objects are only there on even frames. And that's because of the limitation of the hardware that they were dealing with back then. So they basically use 2 neighboring frames, and they average, or they take the maximum of each pixel value. Yeah, and another thing that they're doing is they stack the 4 most recent frames, and this is to introduce the dynamic, the sense of dynamics into the play. So by looking, I showed you. Remember, I showed you the. Just go back all the way back. The network doesn't see these traces. All it sees is the ball and the paddles, and we want the network to be able to tell whether the ball is going this way or which way is it going. So this is the rationale behind having 4 frames.
So by 4 frames means like the input is a 4-channel CNN.
The input is no. They actually take they roll out the entire. Let's see. Where's our? You know what? Actually, I don't know.
It's 84.
Yeah.
84 times
Yeah.
84
Yeah.
times.
So it's like 4. Yeah. Okay. Yeah. Thank you, guys. Yeah. All right. And some other things that they've done to make this thing work was they clip the rewards, so let me first talk about the rewards. So different games have different scores. So in one game you might get a reward of 10 every time you hit the ball. In other games you might have a reward of 1 or something like that. So what they did was they just clipped the rewards at -1 and 1. So everything that's negative or less than -1, they set it at 1. Everything that's over 1, they set it at 1. They also clipped the gradients also at -1 and 1 to prevent the kind of the blow up of gradients. They also select an action every 4th frame instead of every single frame, and then they repeat that action. They send the same action that they chose in this 4th frame to the emulator for these 4 frames that they skipped. The rationale there. Well, one of the rationales I think is that as a human, you can press this fire button on the joystick only every 6th frame. The rationale that another rationale that they give in the paper is that it's faster and cheaper to run the emulator for 1 step forward than to calculate the prediction through the network for 1 step. So that speeds up the training.
So the time steps then, are they every 4 frames, or time steps are still every frame?
Well, because you're collating 4 frames together. That's the state, and you take that. Yeah.
That's why in your image of the architecture, you input 4 frames. That you have. I think you had 4 different channels for it.
Yeah. They don't show the input here. This is the kind of
you have 4 channels, right?
convolution.
You have 84,
yeah,
84
4 frames. Yeah.
Okay, so
yeah.
But it's still stepping 1 frame through time each time. It just takes the next 4. Like, it's not stepping 4.
No, you predict the action for the next kind of set of 4 frames, and then you send the whatever you predicted.
You repeat the action 4 times.
Yeah, you repeat the action for 4 frames.
Yeah, you're 1 frame at a time.
Mm-hmm.
Oh, so you predict 1 action, but you repeat it in 4 frames?
Yeah. Yeah.
Oh, interesting.
Yeah, this is the hyperparameter thing. They have a whole bunch of them. For example, this is a parameter. How many frames do we want to skip? And they again use this informative search, so to speak. That's the algorithm. So putting everything together, you create an empty instance of your replay memory. You set some random weights to your network, initialize the action value function. You copy that, you copy that. This is not 0. These are the status. So you copy that network to your Q hat, and then you go for several kind of game episodes. So an episode is an entire kind of gameplay. So you start playing a game and then you lose or something happens, right? The game finishes. So this is an episode. Then your pre-process that the image that you get, and then you go playing the game essentially. This is the epsilon greedy policy, where with probability epsilon you choose some random action. Otherwise, you have the network predict the action. Feed the action through the network. It gives you back the reward in the next state, the next image. You process that. You store this transition from current state, action, reward, next state in your replay memory, and then you update the network. You select a random meter batch of transitions from your replay memory, and then you calculate the targets, Y. And if the episode terminates, then you set the Y as the reward for this step. Otherwise, you have the reward plus the discounted rewards for the next step. You update the network with gradient descent, and this is another hyperparameter, so every 10,000 steps in their case, they reset the network weights for the Q hat to be Q. Okay, so that's essentially putting everything together in this code model. This is something that they have observed, so how training progresses. These are scores on 2 different games. One of them is Space Invaders, that's where you have to shoot from here. This is, I don't know what it is, but I guess you have to shoot ships or submarines.
Yeah.
I haven't played this one.
You also need to go up to have some air and then come back. You die if you stay
Oh,
too
that's
long.
the one. Oh, okay. Yeah. That's good.
Sam, what about the phone again?
87.
You also drop these kind of the bombs, right? You drop the bombs there?
I think you shoot straight. I'm not sure, but because you have 1 button. Anyhow.
Oh, okay. So this is the score. And as you go through the training, this is what the score. This is the score that the agent is achieving, and this is the Q values that they calculate again on these training epochs on some holdout set of states. So you have the network predict some Q values, and yeah, the pictures show that it learns something. So the score improves as you train the agent.
Is the status space in the left one smaller? Is that why it learns much faster?
Which space?
The left game.
Oh.
Like why does it learn much faster? Is it like the state spaces is smaller?
Probably because I actually don't know whether it learns faster or not.
I mean, Q value is saturated pretty fast.
It also probably, it probably depends on the kind of the complexity of the game, how long it takes to figure out which actions bring which rewards. And here, all you do is you just move this green dot, and just shoot.
I think the submarine has more degrees of freedom. You can go.
Yes, you have to have some kind of more complicated strategy there.
Yeah. And you can actually move in like 2 dimensions.
Yeah.
Like 4 actions in space vision.
So they had 49 games, and the results are that 29 of these 49 games, their agent outperformed human players. So they actually had a professional kind of game tester. I don't know.
How old were they?
Exactly. I don't know what that means.
As old as you.
But these are the games where the agents performed better. So what they did with all these games was they used the same architecture, network architecture, same parameters. The only thing that changed was the output layer, because some games had different. Some games might have 2 actions, some games might have more actions than that. What else is here? Yeah, so that, then see, these are some examples of the games which were super easy for the network, like the pinball, boxing, the Breakout, where it actually learned that the policy that it learned was to make a hole somewhere here first, and then so that right. This is what we want to get. And this one, these ones at the bottom are where the game had the hardest time solving that. So probably the most famous one is, or notorious, is Montezuma's Revenge, where it actually got 0%. So it didn't do better than random play. But so earlier this year there was so OpenAI and DeepMind, they came up with papers that kind of were able to solve the first level of Montezuma's Revenge, but they used human experience to do that. So in DeepMind's case, they actually trained it on YouTube videos from human players. So it's not really kind of what they're trying to achieve here. The problem with this in particular is that rewards are very sparse. So you have to, your goals, this is just the first room, and you have to get to the key. And to get to the key, you have to jump here, I think, jump here, but then get here, get to this rope, and then jump over, I think this skull moves. And you don't experience any reward before you get to this key. So it's a very complicated policy to learn, and that's just the first one. And that could be an explanation. All right, so that's the summary of the paper. They combined Q-learning with deep learning, or a convolutional network, which was able to use high-dimensional input. Previous papers, they were not the first ones to tackle this, the games, the Atari games. But what previous papers have done was manually engineer features based on, for example, color intensity or something like that. So what they did was, the paper did was just send raw pixels into the game and get some output. The techniques that they use to stabilize learning, so that the learning does not diverge or end up with bad values. So experience replay and the second network for target predictions. And as a result, they got this is a generalizable agent that can handle different tasks, meaning entire games, which showed that it can beat human performance in 29 out of 49 games. Okay? So I think this is the moment where we take a break, right? And we come back.
Like 2 minutes break.